Welcome to the lecture Cognitive Systems, and this is still the second lecture. This is the third part of the second lecture and thus the last part of this one. In the last lecture, I have given you some tables as an overview which cognitive functions can be realized on a computer in which way. There have been several terms I have been used and which I have not explained, which are, for example, neuronal networks or ontologies or Bayesian networks. Such things are really important, and so I will give you now a very, very, very short explanation of these things. Not all of them will reappear in our lecture, only part of them will come again. As mentioned before, I will give you a very, very short overview of these techniques just to clarify about what we have spoken. And partly like neural networks, we have techniques which will be investigated a bit closer in the coming lectures. Let's start with the term Markov chains. The Markov chains is a mathematical model, and this mathematical model is used to describe specific stochastic processes. The Markov chain consists of something like states and something like steps in time. So the Markov chain can be used to describe a dynamic system. Think about a chain, like for example, a chain with pearls for a child. So we have those different events which steer the system, or we have these different time steps which steer the system. Very good to be used in a computer. And we also have, as we see later, Markov processes which work with continuous states and continuous time base. But it's very important that you understand the difference between a dynamic discrete state space, which comes from state to state or time step to time step, and the continuous state space or the continuous time base, which is a continuous flow. You can try to imagine this, that in the discrete space you have natural numbers like 1, 2, 3, 4, and in the continuous space you have those real numbers like 1, 1.1, 1.111, 1.1, 1.1, and so forth. So you have an infinite amount of numbers between two numbers, and discrete is only this finite amount of numbers, which is the 1, the 2, the 3, and so forth. The Markov chain is used to describe the probability of the occurrence of a future event. And when you think about this, it's very clear that when you say, okay, I will take a decision in future, we are still in cognitive processes, and this decision which will be taken in future depends on my current state, and probably it depends on all the decisions I've taken before, or all the experiences I've made before, or everything I've learned before. So in Markov chains, you have the possibility to model different things. For example, you can, in the first order Markov chain, model a system where the future of the system depends only on the current state and the current situation. So no history is involved. It's like you're not really a blank page, but you are a page which only has entries for what is yet valid. The n-order Markov chains are taking into account the history. They take into account the current situation, the current state, and n past states. So you can model either a process with a sort of memory, or you can model a process with no memory at all. What I'm not meaning here is a process like a Markov process, but a sequence of steps like in a Markov chain. This mathematical model can be used for both, and it's very frequently used in business simulations, in simple weather forecast. It's used in algorithmic composition in music, for example. It's used for mathematics and insurance companies, for quality management, and also for page ranking algorithms. Very interesting is the fact that Monopoly, the game Monopoly, probably you know it, can be seen as a Markov chain. Next term, the Bayes network. The Bayes network, very, very shortly, is also a mathematical model, but whereas the Markov chain is related to states and to state transitions over time, the Bayes network is reflected by the mathematical model of a graph. It's a directed and acyclic graph which consists of edges and nodes. The nodes are random variables and the edges are dependency or relations between the variables. I will give you an example in a minute. The nodes have conditional probabilities, and the networks are used for calculation of the probability distribution of all participating variables, and that could be really many variables. So the underlying idea is that when you as a human take into account all the aspects of all possible related situations, you still come out with a decision sooner or later, as you have to decide in the end. And this is not possible to be mapped very easily on the computer, this decision-finding processes. For instance, when many variables are involved, the computer still needs a tool, and the Bayes network is a tool to make a calculation which variables have to be taken into account and with which probability a variable is taken into account. It is also possible to embed a priori knowledge into this network, which means that when you know something before you can start the calculation, you can embed this as well. And the Bayes networks are often used for approximation. They are also together used with extensions, and then they can be used for algorithmic learning. As mentioned, I want to give you an example, and this example stems from medicine. In the medical domain, the expert systems, which is a well-known technique, are often based on Bayes networks, and they are knowledge bases consisting of facts and rules. And the facts are represented like the nodes in the network and the probability of the entry of such a node, and the edge denotes dependency. Let's show it. Let's look at the example. When you have, for example, some symptoms like pain in the lower right belly, you have related to this very simple fact. In case you are a woman, you are between 20 and 30 years old, and you haven't had any surgery before, then you have certain probabilities for diagnosis. And potential diagnoses, which are all equally valid, might be an appendicitis, some sort of viruses which is threatening your intertestals, or a pregnancy, for example. Just to mention a few, it might also be an aching muscle, or you have lifted something too heavy, sort of. All those diagnoses, those medical diagnoses, are equally valid. And then comes a priori knowledge. For example, when you are not a female between 20 and 30, but you are a male, then you can simply erase pregnancy from the diagnosis without any effort. Then you still have pain in the lower right belly, which leads to viruses, lifting something too heavy, and appendicitis, which reduces the amount to 3 possible diagnoses. In the end, we want to have 1. And when you then had a surgery years before and you have no appendix anymore, which is in your lower right belly, then is only remaining 2 of those which are equally valid. And if you haven't lifted anything before, then it's very, very likely that you have a virus in your intertestals. So in these expert systems, they try to map the kind of knowledge construction the physician's doing in his mind during work. It's very, very difficult to get knowledge out of the brains of physicians, and so they try to model those probability networks between the symptoms and the diagnosis. It works rather well, but in the end, those medical expert systems have not been the success they could have been, due to the fact that when the expert system has another opinion than the physician, you have a twofold problem in a law problem. Due to the fact that if the expert system says A and the physician says B, the physician says, I am not sure that the expert system, which is a computer, is correct, as I have my experience as a physician. And then when something happens, the physician has to say, I have decided against the computer as I was very sure, and sorry, I have been wrong, so my fault. That's not really a good idea. On the other hand, if the physician decides that he would suggest B and the computer suggests A, and he said, okay, I believe that the computer is right, it's a machine and so forth, then he might decide, okay, I will forget about B and I decide for A. But what if the patient really has B? And the computer simply hasn't had this fact inside of his knowledge base. Then the physician has again decided in a very, very unhappy version. And you don't know this before, so it's better for physicians to get rid of the expert systems and simply say that my idea is diagnosis A or B, and I have not supported this by any computer as I am the physician and I have the most knowledge ever. You see that sometimes expert systems are used for supporting, like for example, diagnostical models, but they're also used for data modeling in epidemiology, for example, in medicine, biology, and sports science. Bayes networks can be found very often, same as Markov chains in work with Professor Kirste, for example. Fuzzy logic, yes, this is also very, 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 very short. In fuzzy logic, you've had two mathematical approaches or mathematical models before, like Markov chains and Bayes networks, and the fuzzy logic is part of a complete fuzzy mathematics. Fuzzy logic is a logic part in fuzzy algorithmics, and fuzzy logic is used for the mathematical description of not precise things like a little bit, a small part, a big thing, very strong, and so forth. Probably you have at home a very modern washing machine, and these very modern washing machines have fuzzy logic sensors inside, and they try to find out by the first water which comes through your clothing in the washing machine. There's an analysis how dirty this stuff is, and then after making this analysis, the machine decides based on fuzzy logic how much of this of the substance for cleaning your clothing has to be used and how much water is very likely to be used and so forth. Fuzzy logic is a generalization of the classical two-value or binary logic. So in computer science, you only have this 1 and 0 binary logic, and fuzzy logic puts more party into this. It puts more numbers in it and more possibilities to be not really A or not really B, but something in between. In the end, okay, in the computer, it's still reduced to A and B, but with a larger space of possibilities. And it allows the processing of vague and unsharp concepts on the computer, which is really very, very important when it comes to cognitive processes. None of your cognitive processes is either 1 or 0. You are not a computer, and everything you decide is like a little bit, a big part, somehow, sooner or later, and so forth. The fuzzy logic theory is based on the fuzzy set theory, which is related to functions and operations, which are all part, as mentioned before, of fuzzy mathematics. Fuzzy logic is used in control techniques, in industrial processes and control, in automatic control engineering, in medical engineering, car engineering, or vehicle engineering in general. It's not only cars, it's also ships and whatever, and planes. And it's also used in the gaming industry. They like fuzzy logic a lot. The term ontology, it's really a complicated term. When you find a philosopher on the street and ask him what an ontology is, he will come with a complete different result than with what you have learned in computer science, what an ontology is. The main term has the meaning the teaching of being, which means the possibilities and the opportunities of being. And being is really everything that exists. The term stems from the field of epistemology. However, in computer science, the term is used in a complete different way. Here also, it is meant to teach the abilities and opportunities or possibilities, of being. But what is meant here in computer science is we use this as the basic functionality for knowledge construction, which means from the philosophical point of view, a very, very sharp reduction of everything. in ontology in computer science means the basic knowledge, the context knowledge, the rule-based knowledge, the semantic knowledge, and so forth. So an ontology in computer science is mainly knowledge about the structure of data and of metadata. Metadata is always the data about data. What kind of data will you find here? Quite close to this computer science idea of ontologies is what we find in categories, for example, in biology. Let's take this as an example. We have had it before when you have a bird in comparison to a mammal. Only when you use the term bird or the word mammal, you still have transported some basic knowledge like how the face is formed, how the babies have to grow, and so forth. And this embedded knowledge, it's sort of meta-knowledge, is communicated by simply calling this up-level category, and how this category is formed and which entries are in it and what are the reasons and what is semantics. This all is part of an ontology. The OWL is one very prominent ontology for steering and structuring terms in computer science. All knowledge models in computer science and in cognitive science use this ontology technique, so it's really a basic technique. Last but not least, well, we have another one, but this is one of the very important things, and we will come back to this one later. We will not take care in this lecture about Markov chains, we will not take care about Bayes networks, and we will really not play with fuzzy logic. We will have a short glance again at ontology, but we might have a lecture regarding neural networks. Don't be confused, sometimes it's called the neuronal networks, sometimes it's called the neural networks. As far as I know, both terms are okay, but tell me if I'm wrong. The basic idea in a neural network, even if it's a mathematical and a computer science model, the basic idea is the idea of cell structure of the nerves in the human brain. The basic nerves in the human brain, well, the basic nerves are 12 nerves. It's not millions of nerves, but only the main 12 major nerves. They are cells, specialized cells, and those cells consist of a cell core and a corpus and interconnections which build a structure like a network between the one cell and the neighbor cell, so that neuronal communication can take place. This idea of neuronal networks consists of nodes, those are the cells, and connections between the nodes, which are the synaptic connections between the nerves. The connections are also called the edges of the neuronal network. What we find here is some sort of circuit technology. One neuron has usually multiple entries and one exit, but when it comes to computer science, we make here more than circuit technology. In computer science, we have one neuron with multiple entries and multiple exits, or a neuron with only one entry and one exit. We have different compositions of this. What is very important in the neural network technology is that we have learning rules which are reflected by the network, but the network is not learning the rule. The network is learning the pattern which is offered, and the learning of the pattern takes place based on the rule which is constructed by the neural network. This is really important. So the network is not learning the rule, but it's learning what the pattern is reflected. One of those learning rules might be the Hebsch learning rule, and there exists different description for artificial and for natural neuronal systems, and also very, very different learning rules. The work itself, as mentioned before, takes place independent of the rule, which means they don't have to develop a rule, the neural networks, but they work directly on the offered pattern. And this is implicit for another aspect of a neural network, which means the logical rules are developed inside the network. This is the training of the network, which means the neural network learns implicitly, not explicitly. Explicit learning would be learning the rule, and after this knowing everything about the patterns reflected by the rule. But the implicit learning is being the rule and trying to match the patterns which are offered. The artificial intelligence networks must be trained correctly to obtain the correct answer or the learning success. And this is the problem. You cannot observe in the pattern what is learned. You can only observe the results of the behavior of the pattern. So a correct interpretation of a pattern by a neural network can only take place when the network has learning experiences with exactly this type of pattern. The problem is if you offer a broad variety of patterns, you have too much noise. And then this leads to a so-called stochastic behavior. So in human beings, we would call this guessing. If you have a very clear test set and very clear possibilities, you have a really good chance that the neural network learns exactly what you want it to learn. But in the end, the problem with neural networks is you never know exactly what it has learned. And now this is really the last slide of this part of the lecture. We have a very, very short glance into Fourier transformation, which is again a mathematical, it's really a very big mathematical field. What we are doing here is we are part of the mathematical area Fourier analysis, which consists of discrete Fourier transformation, fast Fourier transformation, continuous Fourier transformation, and so forth. It's also a very big mathematical field. We have got Fourier series and you've got Fourier integrals, but never mind, we will not look deeper into this. Very important for me is only that you get the basic idea of the Fourier transformation, which is you have a set of incoming signals like in the ear or in the eye. Those signals are discrete or continuous. Never mind, there are different Fourier transformations for discrete and for continuous signals. The incoming signals can be periodic like a sinus curve, or they can be aperiodic, which is also not bothering the general idea. These signals are put together in a signal curve, and this can be processed, and for which also an inverse transformation exists. These are the first steps you have to be aware of, and then the Fourier transformation decomposes the incoming signal in a temporal and a spatial frequency. This is the Fourier transformation, and this can either take place, for example, in image processing, but also in sound processing. The mathematical representation is then a function of space or a function of time, dependent on which level you want to make the transformation. And you, as a human being, and the computer, you can work with this representation of a function of time or a function of space, and this can be mapped and then shown visually, and it's also basis of the most visual analysis processes. Also, Fourier transformation can be used for solving differential equations, for example. That was the last slide. Very, very short glimpses into the basic technology which are used for cognitive processes. You see there is a complete study guide hidden behind this. If you want to be in this, if you want to work in cognitive science a little bit deeper, you still have a broad field where you can decide in which direction you go, and you find always the underlying, very core-specific computer science technology. From my side, this is the end of the second lecture, and I will record the third lecture in a minute.